For part two of section 7.7, we're now looking at word problem forms of questions dealing with what we've been talking about in the past few videos related to maxes and mins. So here's the key to all these problems right here. You have to keep in mind that every time you see the word max or min, automatically that means one thing. Anytime we had a max or a min, as we saw in the last couple videos, that always occurs where a derivative equals 0. So as soon as I see a max or a min, my first response is going to be, well, then I need to find the first derivative, set it equal to 0, and solve for x. As soon as I see a max or a min. So here we go. So a couple examples. The first one that you're seeing here refers to profit. So this was a profit function that was created for selling some units of something. And so you can read through what's going on here, but we are in this problem linking the word marginal with derivative. So this is just a connection to an economics problem, but this is exactly the way that they would solve it based on their vocabulary. So we're seeing the word marginal. That's the same thing as saying max or min, and so we know we're referring to a derivative, and we're solving from there. So for this problem, here is our profit function. And so they're saying X is a certain number of units produced daily. So let's just say we're selling granola bars here. So if we were to produce granola bars and sell them, we're taking a look at the profit when we sold 45 granola bars. We're looking at what happens to our profit. So remember, marginal profit tells us we're looking for the rate of change of profit. And that's where the derivative comes into play. So if we took the first derivative of our profit function, and we sub in the value for x, which in this case was 45. So you can see this is the result that we would see. So how do we interpret that? That basically means that our profit is decreasing at 1 cent per unit if we sell that number of units. That's what's going on there. So remember, this is from a derivative, so we're talking about a rate of change. So it has to do with an amount of decrease per unit, right? We're comparing two things for that rate. Again, on number 2 here, so if we see anything about a max profit, again, as soon as you see the word maximum, you know right away to set your derivative equal to 0 and solve. So if we take our profit function and we set the derivative equal to 0, we're going to get this look here. If we solve for x, we come out with x equaling 40. So that is to say that when we sell 40 units, that is the point at which we are maximizing our profit. And the result of that, so there's two ways this questions could be worded, so you always have to read carefully. They could say, at what number of units is your profit maximized? And that would be the 40. The other wording is the one that you see here in part B, where they ask you what is the max profit. So now that we know it occurs at 40 units, we take our 40 and plug it back into the original profit function to get the profit for 40 units, which would be $1.60. All right, going down with some couple more examples. Here we go with part 2, section A. So the temperature in degrees Celsius after t hours. So they're giving us a function right here where this is going to represent degrees in Celsius, and t right here represents a number of hours. And here's our domain as hours from 0 to 5. So they're going to walk you through this one in steps, but really as soon as I see this for number 3, if I see I'm looking for a max temperature, right off the bat I would already know to do what they're asking me to do in steps 1 and 2, and that is to find my first derivative and set it equal to 0 to solve for t, and all that simply because of this one word right here. So if you find your first derivative, this is the first derivative function that you would come out with, and I'm going to set that whole thing equal to 0 and solve for t. So look at the responses that we get here. We get two solutions. One is 0, one is 2. If I check my domain, both of those are within the stated domain, so both of those are okay to use. So if I were to sub in a 0, so they're looking now for the max temperature, so here's where we apply the result that we just found. Notice I'm not plugging these back into the derivative. If I did, I already know that's going to give me 0. That's not what we're looking for. So I'm looking for a temperature, which is this guy. So I'm plugging a 0 back in for time. I would plug in my 2 for time and check the results that I'm getting from that. So it's either at 0 degrees, could also be at about 5.41 degrees, but that's the two cases that we would identify. right here with a rectangular wall setting. So rectangular region enclosed by 3 sections of the fence. So you can see the 2 sides here, here, and here. It's already adjoining an existing wall. 100 meters of fencing is available. What is the max area that can be enclosed? So in this case, again, as soon as I see maximum, that means I need to identify an area function, find its derivative, set it equal to 0 to solve for x. And so that's what you see going on right here. They start by taking advantage of one statement right here that said 100 meters of fencing is available. That would have to apply to the perimeter or the length of the fencing. So I know that this value plus this value plus this value is equal to 100. So that we can get some kind of a function for that, we're going to refer to these guys as x's because they're the same. And then if I know all these add up to 100, I'm going to say 100 minus 2x can represent this third side of the fence. And so we needed to put those in terms of a common variable so that I can now work with a function for that. And so now if you look at the items that we have, remember this was talking about a max area, so I need an area function to work with. So area we always find with a base times height or length times width kind of a look. So if I did x times 100 minus 2x, I get my area function. And here it is if we simplify. Because they said max area, that means I'm going to take the derivative of my area function, set it equal to 0, and solve for x. Always read questions carefully. Sometimes they might just ask you for this value. They might say, what does the length of your sides need to be in order to receive your max area? And so I would now say, well, they would need to be 25, 25, and 50 would be my side lengths. But this one is saying, what is the max area? So I need to plug this into the area function to see what the max area is. So always read carefully. Going down to the last couple here. Again, drawing these can be some of the hardest thing to do within the problem. So these have already been drawn, and in most cases they are. So that helps a lot. So in this case, we're talking about some wind shelter with a rectangular back. So you can see with the way that it's described, this thing basically has 4 faces to it. We have a left side, a right side, a top, and a back. And so there are 4 faces to this shape that we are drawing. The left and right sides are squares, so that's why those were identified as x by x pieces. But we don't know what this one is. We just know this is a rectangle, so that's where we got to put our other variable. 96 square feet. So remember, square feet would have to be referring to an area. So we're going to need an area function for that value. Then it's saying what dimensions will maximize the space inside the shelter. Well, how do we identify the space inside of a 3-dimensional shape? We call that its volume. So we have 2 formulas at work here. But that's going to make sense because if you look at this problem, I have 2 unknowns, an x and a y. And if I have 2 unknowns, that means I need 2 equations to solve for those. And so that's kind of the first thought process moving forward. So the first thing would be to use this information to get our first function for surface area. So remember, we have 4 faces. I have 2 squares that are x by x squares. So that's this piece, 2x squared. That's the left side and the right side. I also have 2 rectangles, the top and the back. So, and those dimensions are both xy. So here's 2 xy rectangles that we have, and we know the total surface area is 96. Now, we'd have a hard time doing anything with this function because it has 2 variables. So what we're looking to do is isolate one variable so that we can work with it moving forward. So we got y by itself, and that's what gave us ultimately this function that you see right here. So that's one function. But again, it still has an x and a y, and so I really can't do anything with it yet. So here's where part 2 comes into play. We're looking about maximizing volume. And so if I look to maximize my volume, we'd say, well, how do I identify the volume of a prism? And this is an older formula, but it's just length times width times height, or length times width times height. So that's the easiest way to say that. So x times y right here is my volume function. So what we're going to do to clean this up, since I have 2 functions, is we're going to use substitution to solve. So I know that y is equal to this right here. So we're going to sub that in for y in order to get this look. And if I simplify, I can work it all the way down to here. So we now have a function for volume in terms of one variable, which is what we were shooting for. Because it says to maximize the volume, I'm going to take my volume function, find its derivative, set it equal to 0, and solve for x. Now, you know, typically we would say, if I take the square root of this, I have to say plus or minus 4. But in terms of a word problem like this, you can't have a length that's negative 4 units. So we only use positive 4 for x. Okay, so here's where it's really important that you read your directions. They did not say what is the maximum volume. If they did, I would be plugging that back in for volume here and here to get my max volume. But that's not what the question asked. It said what were the dimensions needed for the max volume. And so in this case, now that I know that x is 4, now I'm going to be subbing that back in here and here in order to get a y value. And so x is 4 and y is 8, and that's what's giving me my dimensions. Last one. For this one right here, they're talking about a square metal sheet. So it's a square. So all the sides are the same. And it's going to say, so if you got to pick, this one's a little hard to picture. Picture this as just a flat square. But if I cut these corners out, so I'm going to cut out an x by x corner here, 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 and here. And then I'm going to fold up the remaining pieces. So I'm going to fold this up, I'm going to fold this up, and this up to create a box. And so that's kind of the image that you kind of have to see for this one. One thing to keep in mind on this is a reasonable domain. If this length is 12, and I'm going to cut out some length here and an equal length here, well, that has to be smaller than 6, or I would be left with nothing here, since the total length is 12. And so that's where this statement comes in, so that's something to consider. So if we're going to do volume, again, it's length times width times height. So the bottom of this, if I identify a side length for this guy, right, this is what we are folding up. So for that side length, we would see this as 12 minus 2x. That should say 2x right there, because I'm cutting out an x and an x from that side. So 12 minus 2x would be that dimension. And I would have 2 of those. So that's 2 of my dimensions, is the 12 by x, 12 by x. The pieces that I'm folding up have a height, so picture this as like your height of the shape, of x. And so that's where we're getting the volume function right here for length times width times height, is our volume function. But again, that should say 12 minus 2x. That's what it should have said moving forward. But again, this one's saying maximize your volume. So we're going to look to find the derivative of this and set it equal to 0. So here we are setting the derivative equal to 0 and solve for x. Just a side note, if you're still watching the video at this point, there is a way to solve quadratics in your calculator. If you ever are interested, you can come ask and I'd be happy to show you. It's a great tool on the calculator. You can YouTube it as well. That's another option. That's how I learned, so just an FYI. But if you go on to solve your quadratic, you can see you get values of 2 and 6. Keep in mind what we said earlier. 6 is not reasonable. If I cut out a length of 6 here and a length of 6 here, I would have nothing left because the total length was 12. So we throw out this answer and we just keep a value where x is 2. So this said, what size should the squares be? Well, they should be 2 by 2 squares for this to make sense. This last piece that you see here was just to prove that what we found is actually a maximum and not a minimum. So what you're seeing here is they did the second derivative test. So if they plug in a 2 into the second derivative right here, you can see that they get a negative value, which means it is concave down. So that would occur at a maximum. So we know that x should equal 2 for this.